To determine if you can safely connect 3 breaker-fed subpanels with ratings of 60 amps, 100 amps, and 100 amps to a 225 amp 120/208 volts 3-phase panel, several National Electrical Code (NEC) requirements must be considered. The supply is from a 75 kV ampere 480 by 120/208 volts transformer. Let's break down the key aspects and relevant code references. Firstly, NEC section 408.1. C1 addresses the loading of the panel board. This section stipulates that the total calculated load of the subpanels must not exceed 80% of the main panel's capacity. The rationale behind this rule is to prevent overloading the main panel, which could lead to overheating and potential fire hazards. To apply this rule, calculate the total load of the subpanels. In this case, it is 60 amps plus 100 amps plus 100 amps, which equals 260 amps. Next, determine the maximum allowable load in the main panel, which is 80% of its 225 amp capacity. Calculating 80% of 225 amps yields 180 amps. Comparing the total subpanel load of 260 amps to the maximum allowable load of 180 amps, the subpanel load exceeds the 80% limit. Therefore, based solely on NEC section 408.1, C1, connecting these subpanels to the 225 amp main panel would not be compliant. Secondly, NEC section 408.4. V pertains to the overcurrent protection of the panel board. This section requires that the main panel must have a circuit breaker or fuse that is rated no less than the total calculated load of the subpanels. The purpose of this requirement is to ensure that the main panel is adequately protected against overcurrent conditions which could damage the panel and connected equipment. In this scenario, the main panel has a 225 amp circuit breaker. However, the total calculated load of the subpanels is 260 amps, as determined earlier. Since the 225 amp circuit breaker is less than the 260 amp total load, this condition is not met. Consequently, the existing 225 amp breaker would be insufficient to protect the main panel and subpanels from overcurrent based on NEC section 408.4. B. Thirdly, NEC section 450.3. C4 addresses the neutral conductor requirements for transformers. This section specifies the conditions under which a neutral conductor is required for transformers, particularly in 3-phase systems. The intention of this rule is to ensure that the neutral conductor is adequately sized to carry any unbalanced load current, which can occur in 3-phase systems due to uneven distribution of single-phase loads. In this case, the subpanels are all 120/208 volts 3-phase, which means that they should not contribute any significant neutral current to the main panel under balanced load conditions. However, it is crucial to verify that the neutral bus of the main panel has sufficient capacity to handle any potential neutral current from other loads connected to the main panel. If there are other single-phase loads connected to the main panel, they will contribute to the neutral current, and the neutral bus must be sized accordingly. While the 3-phase subpanels themselves may not contribute significant neutral current, the overall neutral load on the main panel must be evaluated to ensure compliance with NEC section 450.3. C4. Additional considerations include the transformer sizing and feeder capacity. The 75 kV ampere transformer must be adequately sized to handle the total load of the main panel and all connected subpanels. The transformer's capacity should be calculated based on the demand factors and load characteristics of the connected loads in accordance with NEC Article 220. Furthermore, the feeder conductors supplying the main panel must be sized to carry the calculated load as per NEC section 310.15. The ampacity of the feeder conductors must be equal to or greater than the calculated load, and the overcurrent protection for the feeder conductors must be sized accordingly. It is essential to perform a comprehensive load calculation that takes into account all connected loads, demand factors, and diversity factors to ensure that the transformer and feeder conductors are adequately sized. In summary, to determine the safety and code compliance of connecting 3 subpanels to the 225 amp main panel, the following steps are necessary. Firstly, calculate the total load of the subpanels, which is 60 amps plus 100 amps plus 100 amps, equaling 260 amps. Secondly, determine the maximum allowable load on the main panel based on NEC section 408.1 C1, which is 80% of the 225 amp capacity, resulting in 180 amps. Since the total subpanel load of 260 amps exceeds the maximum allowable load of 180 amps, this condition is not met. Thirdly, verify that the main panel circuit breaker is rated no less than the total calculated load of the subpanels as per NEC section 408.4 B. In this case, the 225 amp breaker is less than the 260 amp total load, so this condition is also not met. Fourthly, ensure that the neutral bus of the main panel has sufficient capacity to handle any potential neutral current, as per NEC section 450.3 C4, considering both the three-phase subpanels and any other single-phase loads connected to the main panel. Fifthly, calculate the transformer's capacity and feeder conductor size based on the total calculated load, demand factors, and diversity factors, in accordance with NEC Articles 220 and 310.15. Based on the initial assessment, connecting the three subpoles to the 225 amp main panel may not be code compliant due to exceeding the 80% loading limitation and the insufficient overcurrent protection. A more detailed load calculation and potential upgrades to the main panel or feeder may be necessary to ensure safety and compliance with the NEC. Now let us expand on each of these sections in greater detail, providing specific examples and considerations for practical application. Regarding NEC section 408.1 C1, which limits the load on a panel board to 80% of its rating, it's essential to understand how to accurately calculate the total connected load. This involves not only summing the amperage ratings of the branch circuit breakers but also applying demand factors where appropriate. Demand factors are multipliers that reduce the calculated load based on the likelihood that all connected loads will not operate simultaneously at their maximum rating. For example, if one of the 100 amp subpanels primarily serves lighting circuits in a commercial building, you might be able to apply a demand factor of 0.8, reducing the calculated load for that subpanel to 80 amps. However, it's crucial to use demand factors judiciously and only when supported by historical data or industry standards. In the absence of reliable data, it's safer to assume a demand factor of 1.0, meaning that the full rated load of the subpanel should be used in the calculation. Another consideration is the potential for future load growth. If there's a possibility that additional circuits or equipment will be added to the subpanels in the future, it's prudent to account for this in the load calculation. This might involve adding a buffer of 10% to 20% to the calculated load to provide headroom for future expansion. By carefully considering demand factors and future load growth, you can arrive at a more accurate and realistic estimate of the total connected load on the panel board. Now let us consider NEC section 408.4 B, which requires the main panel's overcurrent protection to be rated no less than the total calculated load of the subpanels. This requirement is intended to protect the panel board and connected equipment from overcurrent conditions caused by short circuits, ground faults, or excessive loads. The overcurrent protection device, typically a circuit breaker or fuse, must be sized to trip or open the circuit before the current exceeds the panel board's rating. In the given scenario, the main panel has a 225 amp circuit breaker, while the total calculated load of the subpanels is 260 amps. This indicates that the existing circuit breaker is undersized and would not provide adequate protection. To comply with NEC section 408.4 B, the circuit breaker would need to be upgraded to a higher rating, such as 300 amps, to accommodate the total calculated load. However, before simply replacing the circuit breaker with a larger one, it's essential to verify that the panel board itself is rated to handle the increased current. The panel board's rating is typically marked on the enclosure and should not be exceeded. Additionally, the feeder conductors supplying the panel board must be sized to carry the increased current, as per NEC section 310.15. If the existing feeder conductors are not large enough, they would need to be replaced with larger conductors to prevent overheating and potential fire hazards. Therefore, complying with NEC Section 408.4 B involves not only selecting the appropriate overcurrent protection device but also ensuring that the panel board and feeder conductors are adequately sized to handle the increased current. Now we turn to NEC Section 450.3 C4, which addresses the neutral conductor requirements for transformers. This section specifies the conditions under which a neutral conductor is required and provides guidance on sizing the neutral conductor to carry any imbalanced load current. In a three-phase system, the neutral conductor is intended to carry the current that results from imbalances in the phase currents. This can occur when single-phase loads are connected unevenly across the three phases, causing one or more phases to carry more current than the others. The neutral conductor provides a return path for this unbalanced current, preventing voltage imbalances and potential equipment damage. In the given scenario, the subpanels are all 120/208 volts three-phase, which suggests that they should not contribute any significant neutral current under balanced load conditions. However, it's essential to verify this assumption by examining the types of loads connected to the subpanels. If the subpanels primarily serve three-phase equipment, such as motors or HVAC systems, the neutral current should be minimal. However, if the subpanels also serve single-phase loads, such as lighting or receptacles, the neutral current could be more significant. To determine the actual neutral current, it's necessary to perform a load calculation that takes into account the types and magnitudes of the connected loads. NEC Section 220.61 provides guidance on calculating the neutral load for various types of occupancies. If the calculated neutral load exceeds the capacity of the existing neutral bus in the main panel, the neutral bus would need to be upgraded to a larger size. Additionally, the neutral conductor supplying the main panel from the transformer must be sized to carry the calculated neutral load as per NEC Section 250.24. In some cases, it may be necessary to install a separate neutral conductor for each subpanel to minimize the neutral current flowing through the main panel. Therefore, complying with NEC Section 450.3 C4 involves carefully evaluating the types of loads connected to the subpanels, calculating the neutral load, and ensuring that the neutral bus and conductors are adequately sized to handle the anticipated current. Beyond the specific code sections mentioned, there are several other factors that should be considered when connecting subpanels to a main panel. These include the grounding and bonding requirements, the available fault current, and the coordination of overcurrent protection devices. Grounding and bonding are essential for ensuring electrical safety and preventing shock hazards. The grounding system provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and to energize the circuit. The bonding system connects all metallic parts of the electrical system together, creating an equipotential plane that minimizes voltage differences and reduces the risk of electric shock. NEC Article 250 provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for bonding metallic enclosures and equipment. The available fault current is the maximum amount of current that could flow during a short circuit or ground fault. This current is determined by the impedance of the electrical system, including the transformer, conductors, and equipment. The overcurrent protection devices must be rated to interrupt the available fault current without failing or causing damage. A short circuit study should be performed to determine the available fault current at various points in the electrical system, including the main panel and subpanels. The overcurrent protection devices should then be selected based on their interrupting rating, which must be equal to or greater than the available fault current. Coordination of overcurrent protection devices is the process of selecting and setting the overcurrent protection devices so that they trip in a coordinated manner, minimizing the extent of the outage. The goal is to have the overcurrent protection device closest to the fault trip first, isolating the fault and allowing the rest of the system to continue operating. This requires careful consideration of the time current characteristics of the overcurrent protection devices, as well as the impedance of the circuits they protect. A coordination study should be performed to ensure that the overcurrent protection devices are properly coordinated. In conclusion, connecting subpanels to a main panel requires careful consideration of numerous factors, including load calculations, overcurrent protection, neutral conductor requirements, grounding and bonding, available fault current, and coordination of overcurrent protection devices. It's essential to consult the NEC and other relevant standards to ensure that the installation is safe and code compliant. A qualified electrical engineer or contractor should be consulted to perform the necessary calculations and studies and to ensure that the installation meets all applicable requirements.